CV of Professor Pandey. So Professor Ashok Pandey is currently distinguished scientist at the Center for Innovation and Translation Research, and also in the CSIR-Indian Institute of Toxicology Research in Lucknow, India. And also he is Executive Director Honorary at the Center for Energy and Environmental Sustainability, India. So he has published a lot of publication. I think he said that now it's maybe more than 1,400, it might be now more. And also he wrote books, book chapter and H index currently 96, and with the station more than 40,000 citation. I think it could be more because it's such a long. So he is also on the Stanford list, top 2% with rank number 8 in the battlefield, of course, number 1 in India. I think without further ado, I would like to invite Professor Pandey to give the lecture. I think Guntur, Professor Pandey is already able to share the.
Yes, Pak.
Okay,
yeah.
Please, okay. Professor Pandey.
Thank you. Can you see my screen, please?
Yes, it's okay. Clearly. Yes.
Very good. Thank you. Thank you, Tjandra, for invitation. And I really feel sorry that I could not join your last meeting.
Yes, it's okay. Then, sorry. Thank you.
Yeah, because you know that it becomes very important. And since it was annual review of the Institute, my presence was a kind of mandatory.
Yes.
So my H index, just to let you know, is now 104.
Oh, yes.
Yeah, and citations are a little more than 48,000.
Yes, yes.
And in fact, on 18th November, probably you might have seen or known, every year this Collaborate Analytics, they bring out the top 1% scientist in the world. And that list is out now on 18th of November, just a week ago. And in that list, obviously my name is there, and apparently I am ranked number 4 in the world, although they do not give a ranking. But since they have taken my interview. In fact, this interview is there on the website of Clarivate. I'll send you a link, and I would want if you could share this interview with your younger. It can be, of course, listened by anyone, but could be interesting for your younger colleagues and students. All right. So I'm going to talk to you now about this lecture, which is on solid state fermentation, opportunities and challenges. This is the title given to me by you. So to begin with, just briefly, I'll introduce all of you my institutes. So this is what we call a CSIR map of India. As you can see, this physical map of India. CSIR has 38 research institutes which are spread in different part of the country, and each of the laboratory has a very different mandate. Altogether, 38 laboratories approximately This institute on the photograph you see on the right side, upper side, Indian Institute of Toxicology Research. This is in the city is called Lucknow, which is the capital city of Uttar Pradesh, the biggest state in India. And in fact, this is very close to Lucknow city is very close to my hometown, about 200 kilometers from here. So it's very different after working 30 years coming back to North, but then I'm happy about it. So this is the a few more detail about my current institute, that is Indian Institute of Toxicology Research. So this institute was established 55 years ago, where its main scope was uh, industrial toxicology, and slowly over the period of time, uh, occupational toxicology also became its activity. And since last 2 decades, we also involved anything it environment, the human that and then sorry, we also have that more than 200 industries we have served. In fact, this is one of our mandate. So more than 200 industries we have served in last 3 decades or something like that. Apart from that, we participate in all the important national mission program which have anything to do with toxicology, and we also are heavily involved onto predictive risk assessment, as well as other kind of risk which are involved uh, uh, into industrial research. So if you look at activities, we have primarily four verticals. The first one is basic applied and operational day-to-day life. So, uh, so this is one of is very common in any research organization. Then we are second vertical with safety assessment and regulatory. We are the recognized by the courts in India on regulatory technology, and if anyone has to obtain by it is not only food material. For example, if someone has to put go for commercialization of any cosmetic products, or any product which is for human need or human use, or any product which is to be left in environment, then it is necessary to obtain regulatory clearance, and we do the different levels of safety evaluation for that product. Then, of course, we are also, as any research organization, human resource development, various kind of basic any research per se. So we take up collaboration and partnership. We have several. It's now 4 years, and little more than 3 years. I am taking care of this center, and we have a large number of startups. Large number in the sense, in last 2 years, 9 startups have been established here, and several industrial consultancy projects, including launching of two industrial products. So one of them is very useful, that is O-Neer. It is a water purification system which does not require even uses of electricity, and it has different modules it's industrial starts up collaboration with researchers, advanced technological solutions. So it may be from our own institute, CSIR, or from other organizations. Uh, so collaborative partnership of intellectual property could be hiring of analytical facilities or what. So different kind of options are there. So this model is one of the new in CSR system, and we are experimenting, and it seems that it is working quite good. So now I'll move on to our lecture topic today, solid state fermentation. So essentially, all of you know, it's a very classical kind of fermentation. It's a cultivation of microorganism under controlled or uncontrolled conditions in the absence or near absence of free water. So the bottom line is that there should not be any free water, and depending upon the kind of feedstock, if we take starchy feedstock, the water content could be anything between 30 to 50 or higher, and if uh, to 20 or even 30. So it's a classical fermentation, has been used since time. We don't have to dwell upon that, but uh, the again products etc. which are currently being produced commercially using solid state fermentation, some mentioned that it's steroid. In fact, it's first commercial initial success of world and single solution or animal stage. So we generally know that it is ideal for growing filamentous fungi, but then in science there are no limitations, and we have proved that even different kind of bacterial culture could be well cultivated and exploited to get quite competitive yield, in fact superior than whatever has been reported in liquid fermentation. So traditionally, it has been used for food fermentation. We all know that the countries in not only in Asia, not only in Africa, Latin America, but even Europe also have been using it for traditional food fermentation. For example, cozy fermentation, and for Europe, when we talk of it, is essentially the cheese fermentation. So what showing the interest for solid state fermentation. It has a much lower water consumption. Water is one of the critical element for the sustainability in the world, and we know that almost 60% part of the world are water stressed today. So if we could reduce the water utilization effectively, that will also not only help in sustainable development, but also lead to less production of industrial effluent. So these are the very important consideration. This is where the world again and again keeps looking at solid state fermentation. So some other information that what are the specific applications where there is a lot of focus and interest for commercialization is in specifically in food now, functional foods and food ingredients, in agriculture areas, biofertilizers, in pharmaceuticals, so functional bioactive ingredients, secondary metabolites, and then specifically enzymes, which have been one of the core commercial strength of solid fermentation. So we are today looking at cellulose production, alpha amylase, protease, etc., and on livestock probiotics for human consumption, probiotics for animal consumption. And if you look at uh, uh, the right side figure, that which organism or which products are being utilized, which cultures are being utilized by which industry. So it's very interesting, and in spite of not being used currently as a high technology, it continues to grow in different parts of the world for multiple applications. So if you look at the pros and cons, when I say it continues to grow for commercialization or for research perspective in different parts of the world, advantages you all know, because all of you have been working into this area, that it has a low capital cost, it has a reduced energy requirement, it has a low effluent generation, it does not have one of the severe problem what we face in submerged fermentation is foaming. And in fact, foam is the one which often causes contamination in large scale fermentation, etc. And also an important fact, as a researcher, you need to know that a question is often asked, why we get higher yields and higher productivities in solid state fermentation. So it's only a speculation, it's only hypothesis. It has been proven to certain extent, but not absolutely, not in absolute terms, that why there are higher yields and why there are higher productivities. Apparently, it is because in solid state fermentation, the microorganism which we use naturally are fungi or some kind of yeast and bacterial culture. And since their hometown, what we often refer in our reference, that hometown, that means the place where we are born, where we are comfortable, where we know the neighbors, where we know the people. So hometown for this culture which we utilize are in solid state, and then it has a very heterogeneous surroundings. And this is what happens in case of solid state fermentation, that the substrate condition is solid and it is very heterogeneous in nature. So apparently this could be related with their better performance, for higher productivities, for higher title. So, in spite of the fact that there are a lot of advantages, specifically, the in the areas where we have very serious concern, that is sustainability, specifically for water, and specifically for industrial effluent, and also about the energy consumption in several parts of the world, including more specifically that developing countries. So, all these advantages add up for the use of solid state fermentation. But then we have several uh, uh, negative points, what you call disadvantages. So it has less automation, we all know, and online monitoring is not possible. What is happening inside the fermentation medium, fermentation bed? It is labor intensive. That means because automation is less, obviously it is a labor intensive. Mixing is difficult, and this is one of the very strong negative point for solid state fermentation, especially when you go for scale up, because then mass transfer is obviously not homogeneous, and there is a heat built up and carbon dioxide accumulation. So these two are one of the are the major negative points. Still not have been able to. This is in fact a very strong chemical engineering problem, and I can tell you that I have been collaborating, still continue to collaborate with scientists from uh, one of the best institutes or universities in the world, from US, from France, from Germany, from UK, and so on, And I've been collaborating with chemical engineers, trying to tell them that this is the issue you have to take, develop kinetic models and look at heat and mass transfer effects and try to understand how this could be taken for scale up engineering parameters and so on and so forth. But then none has been able to resolve this. And until and unless we are able to understand this for scale up, that how to tackle mass transfer and heat built up removal without affecting the growth of microorganisms, without impacting their metabolic activity, both are important. It's just not the growth, but then their metabolic activity to form the desired product is also very critical and very important. So that must be understood, and then only we can go for scale up. And once we are able to understand, obviously there will be drastic change in commercialization of solid state fermentation. So related aspect in this regard is the poor aeration, because the bed is solid, bed is heterogeneous. So we find that the uniform aeration is very difficult. It is related with the particle size, it is related with the interparticle space, and so on. So these are the related issues, and which ultimately lead to difficulties in scale up, and uh, then overall the process becomes very laborious, or we need to develop large number of reactors requiring then higher space and so on. So this is overall fermentation process. We have preparatory step, we have main fermentation, we have manufacturing stages. So raw material procurement, normally these comprise agro-industrial residues. This is one of the advantages, in fact, of solid state fermentation, that different kind of agro-industrial residues coming from different crops, crop residues, or for example, paper and pulp industry residues, and other industries which are essentially agro-based, their residues could be utilized as feedstock for solid state fermentation. That is one of the advantages, because by using them, again, we have two advantages. That one is the cost. We have lower cost, and also second is that we help some way in development of sustainable green process by using them. Then we have the second one is the water act, so the macroorganism. Example is given of here probiotic, but depending upon the need to develop what kind of product we want to study or we want to produce, we have to look macroorganism very carefully. Each of these are very important. In fact, most of the researchers have taken both of these aspects very casually, and that is where we even are not able to publish high quality research paper in today's time when you talk of solid state fermentation, because we need to put our mind into that and go into looking newer aspect and how to define the research in a sense that it could have some novelty, and it could have aspect of developing a process which has IPR, generation possibility, and which could be thought by someone for commercialization. Then water content is again very important. It is related aspect, and macro growth is directly governed by water content. In fact, I will develop on these all details a little in more detail little later. Then functional ingredients. Sorry, there is a mistake in functional ingredients, because depending upon kind of microorganism we are using, we may need to provide a different kind of nutrients specifically for some uh, products. Otherwise, in most of the cases, since we use agro-industrial residues which are rich in organic content, and also which also provide or supplement uh, growth factors, that is nitrogen is there, different kind of trace metals are there. So often it has been seen that we don't need to supplement many things in solid state fermentation medium. So, but in certain cases, we may require to add certain things. Then we have, looking at wind fermentation, we have things to worry about: the temperature of ambient temperature. Obviously, the bed temperature we need to monitor, and we can try to control, but it's not easy. Then we have issues of aeration and mixing as far as possible to do the aeration comprising moist air as far as possible, and if require, we need to go for mixing. But then this is a difficult issue, because if you mix it, for example, if you take uh, fungal culture, they are they have mycelium, and if you do mixing along, since they are interknitted with substrate particle, mixing could lead and rather leads breaking of those mycelia. So, and if the mycelia are broken, it impacts their growth, and it impacts the product formation. So usually mixing is desirable, but need to be controlled at very, very low rate. That is, could be 1 or 1.5 or 2 RPM and so on. So it has to be done, and it has to be thereafter evaluated. We need to study the microbial growth, that how it is being impacted, and it is not the growth only. We need to also monitor the product fermentation, and again, water content. As I say that there are pockets, sometimes there are pockets where there's a lot of condensation taking place, and those places water content become very high, and that leads poor growth or poor formation of product. So that is to be very carefully again monitored. And there could be a situation that we need to do in 2 stages or single stage. In some product formation, anaerobic process becomes secondary. And the first stage, we grow the cells, and thereafter in second stage, we control the gaseous environment in order to produce the product in higher quantities. Then we have control, as I mentioned, that we need to look about water content, temperature, and mixing. And then, of course, the product is there, product isolation and packaging, etc. So let us look at these points in little bit more detail. That, uh, as I mentioned that previously, that macroorganism selection of macroorganism is very, very critical and very important for substrate fermentation processes. And then what we need to understand that what kind of strain selection is very critical and very paramount. If we are not simply taking any strain from environment and simply making a study on some product, is not a scientific study for a researcher who is intended. It may be good for a to begin with, someone starts master's degree, look at the macroorganism, try to understand how a culture is isolated, how enriched medium is produced, how what is the way to look for a specific culture, and so on so much. But then for specifically when you look at PhD student, all that they must first understand that even if you are going to isolate the strain, from where to isolate, there are certain governing principle, keeping into mind what is the main target. One product is main target, or to utilize a feedstock is main target, or what. So strain selection, you need to look at then discuss with a macrobiologist, specifically someone who is well versed with the taxonomy. So we have to keep into mind product properties and taxonomy, product properties and environment, product properties and the presence of substrate, method of isolating organism, it is a enrichment or it is a negative selection. And then also we need to always keep into mind, since there is a human involvement, safety measures. We need to ensure that we are isolating at first point, generally recognized as safe grass cultures, unless and until there is very critical need to look for some organism which even if have pathogenicity, we could handle them provided the lab is in having safety level 2, safety level 3 facilities. So that is the first point to keep into mind when you start isolating the microorganism. Another important point is about strain development. Uh, we know that by adaptation is one of the very important aspects for microbial cultures, and by adaptation we can make several changes. It is never necessary that we look only for genetic tools or molecular tools for modifying the microorganism, because you have to keep in mind that again looking at human behavior, if somebody is not behaving properly, if child is not behaving properly, by love and affection, by some way or other, by teaching in a proper manner, by giving proper food, by providing proper living condition, we can change the nature of child or even of those are grown up, including the researcher. Sometimes we don't get every researcher on the same platform. Someone is not as serious as others. So it is a teacher, it is a success of teacher to adopt that bad boy or bad girl into right path. And this is what exactly happens with the microbial cultures. We need to adopt them, we need to train them, we need to provide them proper feed on right time and so on. Then the culture start behaving the way you want. Obviously it is practically impossible that the the microbe is producing product A and we want it to produce product B. That is probably not possible, unless there is a broad relationship, and then we need to adopt molecular tools to change this property. Then we also have to look methods of strain development. What is, as I mentioned, what is that we are trying to achieve, and which method. Classical methods to begin are the best methods, and we don't have to, in fact, keep looking always that for strain development we need to look at molecular tools or genetic engineering tools. I would not suggest that. Although if this collaboration is possible, it is always good to keep running it as a parallel stream. Then strain maintenance. This is again a very critical element, and in my knowledge all over the world where I have been working or collaborating with the researcher, majority of the people absolutely ignore this point. At times, often transfer from solid medium to solid medium or solid medium to liquid medium, and maintaining on liquid medium is not good. And at time, too long preservation and thereafter transfer is taking place, that also is not too good. So depending upon the nature of microorganism, the transfer should be uh, done. The strain maintenance, what is the temperature of maintenance, and which kind of storage you require, short term, long term, medium term. Accordingly, the things should be selected. And these information are normally available in classical macrobiology book, general macrobiology book. All this information one can find. Or in fact, today is internet time. If you Google it, a lot information you can get. But of course, you also have to use your wisdom to decide the information which has come from Google, which one is the best and which one to be utilized. Not necessary that whatever information you find on Google is all correct. So it is also important that we need to choose right process. I'll give you a very specific example now in next this slide and next 2-3 slides, where strain which have been used using some method. Here example is shown by mutation, and three kind of fermentation techniques have been utilized for them. So it's a strain of rhizopus. As you can see that four kind of mutations were done, and these strains have been referred as R13.5 and so on, right? And when this submerged fermentation was uh, done for an enzyme production, as you can see, the four different strains gave four different kind of enzyme activities. So the best was by the fourth one, But then the same culture, when it was used as surface culture, but in submerged fermentation, the enzyme units are substantially high. If you look at the first culture, they are almost 9 times more, and so on. But the fourth one was, of course, about 1.7 times more. But then when the same culture was utilized in solid state fermentation, if you look at the yields, this was approximately, few hundred times. And here, if you look at the last one, it is more than 120 folds. So this is a judicious, you know, uh, decision to be taken by a researcher, and nothing should be left unexplored, and that is what is called basic research. So there should not be bias for submerged fermentation. There should not be bias for solid state fermentation, and a researcher, anyone who would want to use one of these fermentation, my strong suggestion would be that do not leave out any possibility, any process, because you never know where there is a brighter silver line, right? Now look at this slide. Now we also again are working, need to choose right process. Look at utilization of carbon spectrum. So there is a culture of again fungi, that is this time it is trichoderma viridi fermentation. And so suppose you are exploring that you have a culture and you have been targeting to produce alpha males, and that is how you started looking at isolation of the culture. That is how you started looking at literature, and then did the isolation and so on. So if you have been using these the sources for enzyme production, you found that in uh, different, depending upon different carbon source, enzyme units varied hugely. Lactose, which could be well expected because trichoderma cannot utilize lactose, but then trichoderma definitely can utilize sucrose depending upon the concentration, but it still produced only 17 units per milliliter alpha amylase. And when cornstarch was used in the medium, the enzyme production was substantially high. That because we were looking at amylolytic culture, and obviously when there was starch was there, the enzyme productions were substantially high. But then at the same time, the same culture, when used for protease production, if you look at lactose, so just now I said to you that we know that trichoderma cannot utilize substantially or in a preferred manner lactose. But when you look at enzyme system and the metabolic activity of this culture, we find that it is still produced 175 units, protease enzyme. And when sucrose was the medium, the activities were substantially high, as keeping into a malolactic nature of the culture, 351 units. So equal quantity of protease was produced, whether treatment or the substrate was cornstarch or substrate was sucrose. And in any case, in all cases, the protease enzyme formation was far more high, except when the maltose was substrate than the alpha malase. Now, the, the point is that we were looking this culture for the production of alpha malase. But if you look at this enzyme formation, we can understand the major focus of metabolic activity of Trichoderma viridi was not on alpha amylase production. Rather, it was on protease production, an enzyme which was now not our targeted enzyme. So carbon was wasted. Carbon is being wasted here. Metabolic activity is diverted for for a product which we do not want to produce. So that means use of this Trichoderma viridi for studies on alpha amylase is not worth to carry forward, even if we ended up isolating this culture. That means, so what is the message here, or what we can conclude from this slide, that if you are working on enzyme production, at least you must also look what are the related associated activities, the culture we have isolated is producing. This is very important to understand. In enzyme production, associated activities sometimes have much more relevance than the main product. I'll tell you about this a little bit more when we move on to the last part of the presentation. So then comes the issue of microorganism. This is one of the very, very critical point. I have mentioned earlier also to you that selection of right kind of microorganism is very important. And how do we do it? Now, normally we will refer to literature, and suppose we are interested in production of alpha amylase, and then if you look at literature, you will find to know that, oh my God, I'm sorry, it has a lot of animation. More than 3, 4 dozen, 5 dozen macroorganisms are reported into literature, and several of them, in fact, those which are shown in red font, have been claimed to produce in quantities which are commercially feasible. There are several Aspergillus species without any species name. They also have been reported in the literature as producing significant quantities which are commercially feasible, acceptable quantities of alpha amylase. So this is another slide. We reach up to several bacterial culture. The previous one, this is if you look at fungal culture, normally they produce enzyme alpha amylase which are food application, while for other application, laundry application, detergent application, leather industry application, enzyme usually is from bacterial culture. So if you look at here in this page also, you can see at least 3 cultures have been defined, or you can find their description for commercial applications. We continue the list, and then we still continue the list. So 64 microorganisms are reported or have been reported into literature which produce alpha amylase, and these are the research or patent information. So which one you are going to use? If your target is alpha amylase, so you need to understand firstly the application. If you are primarily looking food application, then it is good to look at fungal culture, and if it is for other application, it is good to look at bacterial culture. And then thereafter we need to produce, if you look at the couple of slides which I showed, that strain selection slides, that what are the parameters we need to consider, then perhaps we would be able to make a right choice. Now we continue on to this one, that need to choose right microorganism. This is one aspect I mentioned about the formation of one product. But if you look at this one, suppose we have a culture and we want to produce, we want to use it. Example is shown here, enzymes produced by, it's very strange kind of animation, sorry. So Aspergillus niger has been, if you look at literature again, has been reported to produce at least 21 kinds of enzyme. And those which are shown in red font in the slide are the one where there are patents claiming that it produces commercially feasible or commercially acceptable quantities of enzymes, these enzymes. So how do we make a selection? Suppose we have a strain, and if you start working only on kinase production, possibly it may produce better xylanases. Or suppose our focus is xylanase production, and we have a culture of Aspergillus niger, and we think that yes, it is producing good quantities. Those that good is very, in fact, dangerous word in scientific research writing. Good, significant, high quantity, these are very relative terms, and unless we define that, how do we claim this good comparing with literature? Unless we define this significant quantities comparing with literature, sorry, it's not very good idea. So again, if we have taken into consideration that what is our main targeted product, and if you try to keeping this slide into mind, also evaluate at least associated activities being produced by Aspergillus niger, then perhaps you would be able to decide that whether my strain of Aspergillus niger is good to produce xylanase or not. Okay. So we move next. Now we have understood all those points very well. So we look at process methodology now. Preparation of solid substrate, sterilization process, rising of suitable inoculum, then inoculation of the moist substrate, incubation in appropriate culture vessels or reactors, maintenance of optimal conditions, primarily the pH, temperature, aeration, flow, method, etc. Then harvesting of fermented solid, drying, extraction of product, and further downstream processing if necessary. So selection of microorganism, I have already gone into great detail. And then we have substrate, as I mentioned, that it depends upon, but normally agro-industrial residues should be taken or utilized as feedstock. Then we go on to process optimization, looking at the basic aspect of process, and then product isolation and purification. In case of enzyme, largely we feel that it should not be necessary at many times to isolate the enzyme. For example, in talk of biofuel production, the enzyme which are produced in SSF, the wet substrate medium directly should be mixed with uh, the the pre-treated substrate for hydrolysis, and we are able to show it that it is far more effective, and obviously it is far more economical. A large number of process steps have been removed, large number of losses have been the enzyme losses have been removed, and obviously the cost have been removed. And then uses of water and the time, etc., everything uh, everything has been removed. So preparation of solid substrate, we know that uh, we need to add water, and when you go for scale up, we should try to avoid using even distilled water. Depends upon if you have the water properties, what is available from municipal supply, your institute, what your pilot plant, whatever. If it has a pH, desirable pH, and much more than if it has not any heavy metallic impurities, heavy metals or calcium, and so much so on. Then we simply can utilize boiled hot water. Sterilization of substrate, as I say that we can go for normal autoclaving method. We require longer time because compared to liquid fermentation, because it's a solid bed, and depending upon the bed height, the time of sterilization is fixed. In fact, this is one of the uh, negative point. Suppose we would like to autoclave a bed of 1 meter. There are reactors. One of the first such reactor was developed in France, where they claim that they can do sterilization without having uh, unsterilized pockets effectively. Uh, but then it could not still get commercialized because of some of the problems. And of course, one of them has been the high cost involved into its fabrication. Inoculum preparation, this is again one of the uh, uh, positive point, because most of the time when you use a fungal culture, we can utilize spores. And in fact, spores can be produced in large quantities and stored at low temperature. So in lesser volume, we can produce high number of spores, high number of inoculum, store it and utilize depending upon as and when required. Even if it is a direct mycelial inoculum, this is also achievable in much easier way when compared to other processes. Then inoculation of the moist substrate. So when it is a product formation, for example, enzyme or organic acid or steroid, etc., it is always good to use spores, and their mixing is not uh, a difficult issue. It has been well achieved at a larger scale. Hmm. But when it is a, for example, a single cell protein, usually then use or silage, then normally we use inoculum of fungal mycelia. And then at times this also poses some issues in the sense some places the mycelial spread is not uniform because of the heterogeneous nature of substrate. Then optimal condition, pH is one point that must be taken very proper care, because you know that if you use agro-industrial residues, specifically if you use uh, uh, solid state uh, bed, there is a uh, there is a this medium have a very strong buffering capacity. For example, if you take wheat bran, if you take rice straw, rice bran, all these have very strong buffering capacity. So it will not be possible. Suppose unlike liquid fermentation, where we take for one normal sodium hydroxide or one normal hydrochloric acid and set the pH of the medium. In case of solid state fermentation, that is not possible. If you add one normal hydrochloric acid and thinking that by this formula, adding this much uh, quantity will bring the pH of the fermenting bed to medium to 4.5, that is not possible because of the buffering capacity of this agro-industrial residues, primarily the crop residues. So in this case, if we have if it is essential to change the pH, we need to look at the pH solution. For example, if the idea is to make the pH of the uh, wheat bran medium 5, maybe we have to prepare a pH solution of 1 and then add in some quantities and then see if the pH has changed or not. Same thing is if you want to check take pH to 9 fermenting medium, that is solid bed medium, then we have to use a very high alkaline solution to set the pH. So in fact, this should be taken as one point in favor of SSF, and that is effectively what happens when you are concerned with fungal growth in medium for enzyme production, etc. We don't have to precisely, we don't have to worry about pH. Temperature is important aspect, and temperature of fermenting bed is much more important, and we need to understand that there could be pockets because of accumulation of carbon dioxide. There is a because of the uh, aerobic nature, there is a respiratory action, and then we today we know very clearly that how it happens, and then uh, depending upon the efficiency of the uh, you know, aeration, the temperature could be well controlled. Limiting factor obviously is the bed height, bed thickness, and we cannot go. Uh, in fact, something like 7.5 centimeter today is considered as the maximum, which could be utilized in a normal tray kind of fermenter and so on. Then harvesting of the fermented solids depends upon, suppose if it is a single cell uh, protein, nutrient-rich protein for cattle feed, etc. Nothing is to be isolated. For enzymes, as I said to you, today for biofuel application, it is highly, you know, desirable that we use the solid wet fermented material. That means the enzyme production should be carried out at in situ, wherever the plant itself should have in a module to produce enzyme, and the fermented mass should be directly added, used for or added into hydrolyzing medium. Then there are again situations where drying and extraction of product is required. For example, you want to produce enzyme, and enzyme should be, extracted using a different way, normally water or with saline, and they should be dried. Uh, you, uh, there could be some filling material, etc. These are commercial secret, and nobody would like to uh, share them. So normally these are the four cultures which are predominantly so far have been reported in different product formation, except some patented specific processes where they would not like to reveal the specific name or of the culture, because by patent regulation it is never necessary. You can say biological agent, say a specific biological agent, property describes property and give its accession number in patent depositories. So now let us start with a specific example. That is, we know that cozy fermentation, in fact, it became so much phenomenal that for a large number of years, people have been talking SSF as a cozy fermentation. So all of you must be knowing that what is cozy fermentation, how it takes place, and it is one of the very common in East Asian countries, and commercialized centuries before, and so on. So what are the processes, the kind of setup, some other details are given here. And enzymes involved are essentially alpha amylase, glucoamylase, and acid protease, but then there are several associated activities, and that is how koji from one industry to other industry is very different, and the product is also very different. And some products are become very famous or liked much by the consumers, and it is only because the associated activities which I mentioned in the beginning to you are very different, and some are able to utilize are utilizing some cultures which produce very desirable associated activities. Associated activity means the production of different other enzymes in a small quantities. So koji fermentation again, what are the other steps and more details. Refinement is also considered as one of the very, very important aspect, including what kind of fermentation or filtration process we are employing. So in fact, people still believe much more in cozy process, the traditional way, rather than looking at for some newer aspect. There are moderation, there are developments, but then it is primarily governed by the traditional factors. So if you look at this one, the fermentation process creates over 200 different flavor compounds. So this is what is very important for the successful production and commercialization of cozy. So process parameters, if you look at which are the process parameters, we need to control at chemical factors, as mentioned, that nutrients, very important, growth factors, temperature and oxygen, and then biological factors, microorganism. We have already discussed these points. And in the process, if you look at a specific characterization, that solid matrix, different kind of feedstock, and of course rice bran, wheat bran is the most common. Then we have liquid medium. Basically, it is a mineral medium. Sometimes nitrogen is also supplemented, and depending upon the nature of rice bran is different, sawdust is different, sugar beet pulp is different. So depending upon their chemical composition, about their minerals content, we need to add additional nutrients. Inoculation, that depends upon what kind of process you are using, product formation using. Then we need to decide doses of inoculation. Temperature, again, depending on the product formation, it could be as low as 5 to 95 degree. And also it is directly related with the microorganism which are using. The moisture content, 50 to 85%. These are, a range given, not necessary that everything will be primarily defined by these parameters only. Agitation, it could be mutant, it could be no agitation, and it could be a constant rotation depending on the kind of reactor system we are using. Then if you go for aeration, 0.5 to 5 VVM, and duration could be up to 24-hour or fungal fermentation. For example, if you're looking some enzyme, it could be as high as 5 days. Also, it depends directly with the kind of microorganism and product. Cellulosis production takes longer time, and xylanalysis by bacterial culture takes much shorter time, and so on. Downstream processing, none or centrifugation for many applications. Process parameters. So the size of substrate particle, in fact, this is one of the very important aspects, because we have to keep into mind that when you use a smaller particle, they provide larger surface area. In solid state fermentation, whatever microorganism we use, they normally grow on the surface of the substrate particle. And so larger the surface area, larger will be a space available for the growth of those microorganisms. But then smaller particles, even if they provide larger surface area, they also create a compact bed. And if the bed is compact, there will be difficulty in aeration. So it is not a very good situation then if you are not able to do aeration. So air penetration will be one very big issue. But then if you use bigger particle size, the bed would be much more, porous, wide volume will be larger, and aeration would be easier. But then there will be lesser surface area available. That means the space available for the growth of a microorganism will be less. So both are contradictory. We want as large as possible surface area, but then we also want proper aeration to take place. So from this we understand that we need to make a compromise. And this is again one of the very critical scientific and wise decision to be taken by the investigator, that what kind of substrate particle we have to use. It has to be a mix of small to smaller and then big to bigger. And this is where you have to do the experimentation and understand that the level of particle size and their mixing. We also have to understand substrate characteristic, that excessive water tends to aggregate on solid particle, making aeration difficult. And when the aeration is difficult, the growth will be impacted. And low moisture environment fears growth and yeast and fungi. So this could be well understood if you keep into mind the aspect of water activity. If you look at water activity of microorganism, that is scale, water activity is theoretically one of pure water, and the water activity factor required for the fungal growth is much lower than bacteria. So normally bacterial growth is well around 0.9 water activity. That means the water should be free flowing. And this is how the basic information or basic definitions and thoughts of solid state fermentation were there in the olden time, that bacterial cultures are usually not good for solid state fermentation. But then in science, nothing is impossible. And we have proven that by adaptation and by manipulating the growth condition and engineering the medium, we can very well cultivate bacterial culture into medium and produce different kind of products. We have shown it for lactic acid production. We have shown it for different kind of other products using bacterial cultures. So the yeast and fungal culture, depending upon the the kind of strain we are using, the water activity could be between 0.5 to 0.7, or even in certain cases 0.8 or 0.85. Specifically, we are looking at the fungal cultures which grow on cellulosic feedstock, rice straw, wheat straw, sugarcane bagasse, and so on. So in this kind of fungal cultures have higher water activity requirement compared to the fungal cultures which grow on a starchy feedstock. And same is true for yeast. Normally, yeast require 0.5 to 0.6 water activity. So water control in the medium is important, and this, in fact, is done by spraying intermittently water. And if there is a mixing also, then it can be well controlled. And together, both of them remove the heat, as well as with forced aeration, we also remove moist aeration, and we also remove carbon dioxide. So from this, once we have understood that the microorganism, the feedstock, that is substrate, and the process parameters, now I'll take another few minutes to talk about design of bioreactor, and then we'll come to the last part of my talk about what we have been doing as a briefly telling you what we did and where we have reached. So SSF is mostly the process we know at least commercial scale are batch processes, and different kind of bioreactors have been utilized. But then mostly it is a tray kind of fermenter. The concept still evolves around that. It's a very traditional design of tray fermenter. You can see here, and it's another one that usually small, often simple reactors, and small or medium scale, because as I mentioned that we still do not know how to tackle heat built up carbon dioxide removal in larger bed size, and also the still the issue of sterilization continues with larger bed size. So tray bioreactor is one of the most common reactor we utilize in SSF. Also, there are a large number of reports, and this also has been commercialized. In fact, for food processes and other, especially for food processes, that is a kind of packed bed reactor. We have been working in different kind of packed bed reactor, horizontal, vertical, and so on. And although there has been always issue even in this reactor about the scalability. In this, mixing is very well possible, and the traditional drum kind of reactor, which resembles like a packed bed reactor, I'll talk about that also little later. But then the biggest weakness is that bed depth, we cannot go much high even in large reactors. Cylindrical drum kind of fermenter is the one which I mentioned, and it has been also commercialized for multiple application. In fact, specifically for development of single cell protein. And as you can see, as the visual figure is there, rotating drum and stirred drum. This stirred drum kind of reactor, we have airflow, we have rotation, and we have material. So this ensures that with these pedals which are present into this system, that the medium keeps moving, and then there is no agglomeration of the medium particle, and also there is no blockade of carbon dioxide, etc. Here we have two ways to control the temperature. One is that we keep running in a jacket, cooling or hot water, and the other one is that we keep passing in this central pipe where the air is there, moist and sterile air. So that also takes care of bed drying. So this has some automation that you have possibility to keep reading at what is the relative humidity at real time and what is the uh, you know, temperature. Temperature of bed can be monitored continuously. Temperature of the gaseous environment in the chamber can be monitored, and those gases can be, you know, uh, can be utilized for determining the growth of the culture using the respirometric principle, which are very common today to determine the growth in solid state fermentation. Some other design that is primarily what we refer as stirred aerated bioreactors, that we have the first one is looked at stirred aerated bioreactor, the gas solid fluidized bioreactor, and then we have rocking drum kind of bioreactor. And on all of them, there could be possibility of forced aeration with moist air, which can take care of heat accumulation, carbon dioxide accumulation, and also possibility of sprinkling the uh, water uh, in the sense that uh, the air can be moistened and so on. This is the other example that bioreactors, so that rocking drum bioreactor. This is also available commercially in a small size. The first one is usual week, that how it is there, and then second one is you know, what is happening inside, that rollers etc. are there, and so this is also this being manufactured but only on a specific order given by the client, and this is very compact. As you can see, this is how it looks like. So when you want some automation and we want to move from laboratory process to some level of scale up, this is one of the important development, and this reactor could be utilized for enzyme production, for other product formation, etc. This is basic design in all kind of this 3-4 reactor I showed to you, that and with much more automation. We have exhaust gas analysis, no, possibility, online monitoring. We have liquid supply possibility. We can spray it. We can pass through the moist air. Then we have in the center pedal type for mixing, because this is the one which is considered most efficient, even not to damage the mycelia. And if it is a, in fact, in real time, we can also continue to extract the product when it is formed into the medium by, you know, simple passing through the liquid, that it could be saline, it could be just water, and then uh, monitoring of growth, monitoring of temperature, monitoring of uh, medium uh, humidity can be online. So this in a setup, how it looks like, that what are the things we require in a laboratory, that we require obviously to stock the culture. In a cold, we require cold room for feedstock, etc. Clean bench for aseptic work, incubator, and then different kind of other fermenter, etc. And uh, what kind of fermenter you would want to buy, and what are the avenues for you to procure it. Several pellet kind of pellet plant kind of reactors are available in the market, or they can be constructed according to a specific requirement of the institute or the group. So look at the scope, that still the question comes. The potentially many high value product, including primary and secondary metabolite, are still being exploited all over the world, and there are different kind of successes uh, depending upon the interest and report. A large number of patents are still being filed continuously on high value products and secondary metabolites. But then we could increase the scope to bioremediation and biodegradation of hazardous compounds, biological detoxification of agro-industrial residues, biotransformation of crop residues, etc., biopulping. And in fact, biopulping again has been adopted by some of the paper and pulp industries. The proposed configuration that specifically when you talk of second generation uh, bioethanol, and when you talk of in situ utilization of the product, as I mentioned to you, that after fermentation, we don't have to follow all this step. That the cultivated fungal culture directly can be admixed with biomass for saccharification, and this is one of the thing already being, put in some places. I know some places in Hungary, some place in which is a facility of Novo Nordisk. They have put it, and it is being put in India as well, and in Mexico also. One of the Altec manufacturing services, which has put, which is enzyme manufacturing, which has put a demo plant for ethanol, bioethanol, and they are also using that fungal cultivated directly this entire biomass mixing with uh, feedstock for saccharification bioethanol production. So with this, I'll now go to the last part, that what we have been doing, that solid fermentation research and technological development and industrial linkages, what we have been doing at my previous institute, and to some extent I continue at my current institute. So basic studies we need to do that. This example I'm showing that this was one of the first study. We could show that crude trichoderma harzianum, which produces chitinase enzyme, and which arrested the growth of heterogenic pathogen called trichum by breaking the hyphae. So this is the control one, and this one you can see when it is growing, the mycelia are broken into different places. So so this was very good example to show by SEM, and then we carried out large scale production and very positive result, and then we did within industry actually field work for its commercialization. That's one example I have shown, but uh, we have several patents on SSF. We have commercialized several, and then many enzyme and leucine production by Streptomyces, one specific strain. Then methionine aminopeptidase production by again a Streptomyces strain, and then phytase for feed application. This has been commercialized by Aspergillus niger. Food grade alpha amylase using Aspergillus niger, again commercialized, transport industry. Then paper and pulp industry specific requirement for xylanase, again commercialized. It was through bacillus culture. Then we have also done inulinase by Staphylophilus coculus species. Then fungal spores. That is how we showed that spores could be cultivated in large quantities and stored in the required conditions. And glucoamyl. This was, of course, the first enzyme we started to work on to this one. These are the four technologies we have transferred to industries. Alpha amylase for food application. And in fact, as I several times I mentioned to you that associated activities. So in this particular case, it was the associated activity which imparted very desirable taste and odor, or whatever you can say. The aesthetic value of bakery product increased substantially by the industry, and that is how it was taken. Not that the only the enzyme yields and productivities which are important. So associated activities are very important, and if you work on enzyme, you should never ignore them. Then we transferred that xylanase, which was cellulose free for paper and pulp industry, and then we again transferred a feed enzyme to for which is produced by Aspergillus niger for feed industry. And the next we transferred was a specific cellulase for de-inking application using a fungal culture. It is it's a mutant developed by us, but mutation doing a traditional X-ray mutation. We have done several other consultancy projects for enzymes, chitinase, as I mentioned, at large-scale field trials, endoxylenase for another paper and pulp industry, and nitrase and lipases for a specific application by a biotech industry. This I have already mentioned to you. So in fact, if you do keyword-based index search, you'll find that on solid-state fermentation, we are the #1 in terms of SCI publications. This is what is shown into Scopus. We have put a pilot plant in our institute, that is at Center for Biofuel in NIST, and this is completely automated modular system. Depending upon the requirement, we can use 1 module or 2 module, and the batch size is 50 kilogram material. It is essentially based on tray, that is we utilized perforated tray made of aluminum, and as you can see, this is a control system. It is completely the entire fermentation system can be controlled and monitored for parameters which I mentioned using computers. And one of the strongest thing that we have all over the world, we have this kind of collaboration in started with Brazil and then France, and then everywhere into world, more than a dozen countries or more than 15 countries, we have collaboration. Somewhere it is over, somewhere it is still continuous on solid-state fermentation, depending upon the product, and interests are very different, but it continues. So the last slide before I thank Professor Setiadi, that science happens when people seek to discover their place in the world. Solid-state fermentation has been researched by hundreds of thousands of people. People keep looking still, but only those who want to make a place in the world. And then from this perspective, they look at SSF in a very different manner, keeping into mind the basic aspect which I have shown you about the microorganism, about the medium, and so on into consideration. So then only you will be able to develop a novel aspect or new aspect in SSF. Otherwise, it continues to be, simple, SSF studies which have no novelty. So think a bit more, read a bit more. Unless you read a lot, you would not be able to understand which way to design the your SSF in order to look at IPR issues, and in order to think of application of product for commercialization, which is a great need today all over the world, and much more so for developing countries, and including Indonesia, of course, including India as well. So I'd like to thank Professor Setiadi for giving me this opportunity to share my views and some scientific discussion on solid-state fermentation. So thank you very much. And if you have any questions or anything you want to discuss, I'm available. Thank you.
Thank you, Professor Pandey. So we will have some, I think it's a question. I think Guntur could help us.
Yes, please.
So that one is the question from the audience. This one from Hendro Tjandra. So I'm interested in bioprepping research or biodelectrification using the SSF method.
Yes. So Hendro, this is it's a question which you have to tell them pros and cons. Biodelignification, obviously, is a slow process. It can be fastened by increasing the quantity of enzyme. Of course, it is not possible that you use X quantity and then make it 10X, and thinking that the speed of pulping will also increase 10x. There is a limit, but then this is the first aspect. So what are the advantage biopulping process will offer? This they have to keep in. And one of the major aspect is the environmental sustainability. If the industry has no interest into that one, it will be practically impossible for you to make them understand that or make them interested. And so environmental sustainability is one parameter which cannot be you know taken into account in quantitative terms. It can be taken up. It is being taken up in European countries where carbon footprint is being looked into, the greenhouse gas emission is being looked into, and the impact on environment by discharging hazardous effluent is being looked into. So uh, eh, you have to make them understand that what are the basic advantages. It is just not only one consideration of economics, and it is just not consideration of only the time which is being taken, because you can modulate your process into batches according to size of production of the industry. And then similar way, in similar proportionate way, like one single stage and two stage system you can develop, and the biopulping process can staggerate into many modules. No, today you start with one batch, tomorrow you go for the second batch, and then they may take a longer time, but even then, taking into account the size of industries, industrial production, and fractionating into some part, and then making biopulping process, batch process, uh, taking into account your residence time for the treatment. So these are the two options available to you. There is no other option. And this is where, if the industry is cooperative, industry is able to follow it, the scenario will change. But then you have to try taking these two scientific component as well into mind, right?
Okay. Just move on to the second one.
Second one is the kinetic model. How to
Model.
spirometry is a simple model which you have to utilize for the determination of mass of fungus. You don't have to separate biomass from it. Is impossible. No one can separate any kind of biomass, whether it is a fungal, yeast, or bacterial. And indirect estimations are the one which are taken place. So you can also continue to use the traditional method of looking at you know uh, uh, estimation, chemical estimation. But if you are able to create this uh, simple system which are described into literature, that is the most accurate way to determine the fungal biomass.
Okay, then the third one is about the inducer function.
Yes, inducer function on fungal inducer function, it depends upon firstly what is the culture you are using, what is the, is it, for example, if it is a product, uh, and if it is a culture which requires some induction. If it is a inducive enzyme, and if the medium does not induce it, medium component do not induce it, then obviously you have to look at some inducing product. But if you can have, if you can tell me your specific question, that what enzyme you are looking, what product you are looking, what culture you are using, what substrate you are using, probably I can tell you something more.
Okay,
So,
yeah, it might be you may so that he, I think so. Dia, or you like to add more?
Yeah.
you can ask me even later. You can give your question to Professor,
Yeah.
and Professor, you can send it to me. We can continue. It's not that it is just over today. We can continue. Yeah.
Yes. Okay. Probably the next. Probably we move on to the next question.
Yeah.
Guntur, please. Uh, that one is from Mustafa.
Yeah.
Within.
There is a direct relationship between the moisture content, but you cannot take moisture content stand alone. You have to also take into account water activity. That is much more important aspect, because both are interlinked. It is the gaseous moisture content which is in equilibrium with the substrate moisture content. That is what is uh, taken into account, and that is what together governs the microbial growth in solid medium. So water activity is not a very difficult aspect to determine, but those of you who work on SSF regularly, you must obtain the equipment that is a water activity meter. It is a simple equipment, and you just need to put into your you know system, and this will give you direct reading. It is a handheld system. It's not expensive. I do not exactly remember the cost, but there are several companies today into uh, manufacturing. So please consider water activity together with the moisture content, because that is what it is not simply that 5 well medium, and that will tell you the moisture content present in the medium, but not it will correlate with the fungal growth. Okay.
Okay. And the next question from Reti about the solicited fermentation for the
Yes.
pharmaceutical products.
So let me tell you that let me go to the history back. The first solid-state ferment, first antibiotic in the world, it was produced by solid-state fermentation only. That was when we learned about what you call wonder drug penicillin, which was it was referred as wonder drug because in Second World War it was used like what you call as a magic drug, because there were people soldiers were getting infection, and by application of uh, penicillin, practically everybody was getting cured. So that is how it was called magic drug or wonder drug. And this was produced, interestingly, by solid-state fermentation. But then it was it were the scientists and the researcher of that time, for some reason, never inscribed into literature. They started working more on submerged fermentation, and then the whole world moved towards submerged fermentation, and SSO got neglected. But then we know that secondary metabolite are the very interesting product to be produced using solid state fermentation. Huh? So there are a large number of patents still, as I mentioned to you, being taken. And what is very interesting that many product which includes primarily secondary metabolites and much more so is enzyme. It is never necessary for the industry to reveal which method of production has been utilized, and so they never reveal that which is the production system they have utilized. In fact, if you look at enzyme industries all over the world, the biggest industry, which is Novo has the most modern SSF reactors, and of course they have submerged fermentation, but they never reveal which enzyme has been produced by which method, because it is not required by any law or any regulation by any country to reveal the method of production. And it is so most secrecy, because it is a very very competitive world, so nobody would like to reveal. I know many industries. I have visited Altec industry, the US based industries all over the world. Novo I have visited many industries. Every of them is having submerged fermentation as well as solid fermentation, and they don't reveal exactly what they are using. So this is very interesting. That it's very good that your topic of secondary metabolite, but then you have to be very specific which product you want to look at and why you want to look that one, and what are the microorganisms you have available or you are going to isolate. Unless you have a reasonably good microorganism, it's not very good idea to move on to such processes.
Okay, thank you. And then the next from Brian is the industrial practice in disposing the solid waste from the SSF.
This is, in fact, there is no disposal. This is one of the
Oh,
again advantage, because in practically every solid fermentation, we utilize only grass culture, generally recognized as safe. So when it is a fungal culture, you can utilize this for multiple application. You can otherwise, if nothing is there, multiple application. If there is no inhibitory nucleic acid content, it can go as a feedstock, or it can be further used as for composting and so on. There is no waste generated from solid state fermented material.
okay, thank you. So, Guntur, could you the next page, please? That's from Rennie. Uh, it's difficulty to grow the microbe in plastic media. So
You
that,
should not have difficulty there. Again, here you need to look at specifically the surface area, and there's this very. If you look at large number of studies have utilized plastic media, which have what you call pall rings. That means they should have hole in between, and the medium should still require some kind of support. You cannot simply pour your liquid medium onto this one. Otherwise, so it could have, for example, you can supplement it with uh, some gelatinizing agent, which do not have, which the microorganism itself cannot utilize, and then uh, put into liquid medium. You can use you can use agar, for example. Melt it at, you have to use a specific agar which melts at 32 or not more than 35, 37 degree. Put your pre-inoculated nutrient or the medium, liquid medium into uh, agar medium, 1% agar or little less, 0.7% agar, and then pour onto plastic medium. Then trickling medium, then it should grow well.
okay, then it is from Pena regarding the amylase. So the question is, it has an associated activity, and I think come to the additional selling value for the bakery industry. So that it might be there's another values, not only selling the amylase.
Haha, this I cannot tell you. This is trade secret.
Yeah.
It is.
Good.
I'll tell you that how we have to do it. Firstly, we need to look at enzyme spectrum. This is not very difficult thing. You need to look at look at literature, what are the enzymes reported, and thereafter look at your own products spectrum with different kind of carbon sources, and this will give you good clue that what is the metabolic activity, uh, what how much metabolic activity is being targeted onto main product formation, and then which are the other enzymes being produced, even if they are in traces. And then that is how you have to look a specific application, whether it could go for paper and pulp industry, whether it could go for food application, and so on.
Okay. Okay. Then from Guntur, actually, the question is about so the effect of the aeration in the solid state fermentation.
Oh,
How? Yeah.
this is a good question. But then, uh, in order to determine that how efficient is the method, you have a control system, a flask always running parallelly, or in a system where you have not done aeration, control system without aeration. And if you look at a total carbon present in the medium, then you have some idea that what are the yields and what are the productivities. And then uh, you have to start looking at zero point 0.1 VVM and so on. Obviously, you cannot do a large number of experiment, but if you go on to that factorial design kind of experiment and develop the models and to see that how many runs can be done and then minimize the effective runs to ensure taking into consideration which aeration rates are significant. And that is how it is determined.
Okay. Then, thank you. It's still, I think, it's a question, Guntur. That one is a. Uh, what is the easiest and the cheapest bioremediation technique for the management of polluted? So that's one for the soil bioremediation.
Yeah, this is again very important, and this is where we have uh, quite good success. In fact, we have been able to remediate even uh, highly toxic soil.
Mm.
In my own city, we had industries which have been making pesticides, and pesticide had been simply disposed into open environment, and there have been no regulations. And inside the industry, nobody bothered. And also, the problem of not abiding by the law and bribing the inspectors and so on. So there is a large area, more than uh, close to 100 acres and all that, which is simply now uh, closed with no entry for the people. And with the intervention of Supreme Court, then we could get the sample. We did the study, and since last 3 years, we are doing field work on remediating this. So we prepare a bacterial consortium of different Pseudomonas species, and we make a small field plot of, for example, 50 by 50, and then increase it to 200 by 200 feet. And we spray this culture on the top layer, and then we mix it. And we do not do any aeration, and we leave it, but then we keep controlling the moisture. We do moisture supplementation in between. We don't supplement any other kind of nutrient. And after every 10 days, we keep looking at the residual this pesticide. And now we find that in approximately 30 days time, we are able to remove close to 75 to 80%. But that is the limit. Even after 40 days, it remains still the same. So even if you are able to receive 70 or 75%, this is a great relief. And then this topsoil could thereafter be removed, and then we can go on to looking some other way to remediate remaining, So this is very important, topic. And if you could work on to this, Ronnie, it will be great help for you, for the nation. You must try it in a larger way, but then look at specific uh, chemical which you want to remediate, and then accordingly from the literature select cultures. If you have your own cultures, that's the best thing. Otherwise, look at cultures available in culture collection where there is no IPR restriction. Then develop your own consortium. It's pure culture is very difficult. Consortium only. And look at if the soil which are going to remediate, if it has still any culture. If it has still any culture, that will the best to isolate, enrich, and adopt, because that means the culture is growing under the adverse condition and probably using that pollutant as carbon source for its growth and survival. So that is how you have to look into this one.
Okay, thank you. Then that one is from Rainy again. So that one is to decolorize the textile waste water using the SSF with a white rot fungi to remove the azo dyes. The color was clearly removed, but the SCOD was increased. Any suggestion?
In fact, when you say color was removed, it is in fact uh, the first you need to look at what product were formed. We know several time, not all the time, but several time we know that when we degrade this kind of azo dyes, there are formation of smaller molecules, and in fact, sometime they may be more toxic even than the azo dye itself. So the first we need to determine what it is not that the color was removed. Color removal is one parameter, but what were the product which were formed, you need to determine first that. And I cannot understand this one how COD was uh, increased, because this must be, in my perception, an experimental error, because experimental error. The carbon content cannot change. The total carbon content would remain the same, whether it is a azo dye or if it is a something else. In fact, it should reduce if the culture is aerobic and if it is utilizing azo dyes as carbon source for its growth. So some carbon will be used for biomass, cell biomass formation, but at very small quantity. But then definitely if it is aerobic culturing, carbon will be utilized for carbon dioxide formation. So COD cannot increase. This is a big question. So you need to look into this again and try to see that where something is going wrong. I don't know which COD method you are looking. One solution could be that you look at total carbon at control that time 0, and thereafter carbon at different time of intervals, which will give you a good clue whether your COD removal analysis, COD analysis is correct or not.
Okay, I think one is the last question, Guntur. It might be we already almost up to the time, but maybe the last question, Guntur.
Okay, wait a bit.
Oh, so that from Francisca.
Yeah, so when you work on shell waste, you need to first look at what are its chemical composition, what are the and accordingly you have to first find a culture which could utilize them primarily as its growth for its growth. So the idea is, what is your idea? You want to utilize shell waste for any product formation, or to or to simply its disposal. That's the first point you have to determine. Or you want to use the shell waste for formation of some other product, a specific product. So that is how you have to look at the microbial culture for growth and activity. Do you have a Do you understand my point?
Yeah.
Do the
It's
chemical analysis of the waste. Look at what are the chemical components of this waste, and thereafter determine what is the kind of carbon source from in this waste which can be utilized directly by the culture. If the carbon source cannot be utilized directly, you might need to supplement some additional carbon source in order to initiate the growth of culture, and thereafter see if the culture can utilize the carbon source present uh, in the waste, or grow a culture which supplementing small quantities of carbon source, which produces some enzyme or some organic acid which can decompose or degrade shell waste to a smaller molecule where some carbon source may be available for growth and activity of the culture.
okay. I think we are already close to the 12 in our time. So I think I would like to thank you to Professor Pandey. It seemed that the 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 interest of from the student and also from our faculty members is very high. It may be next year I would like to ask you again to give more technical or more research regarding the solid state fermentation, or probably your idea in the more technical one. So I would like to thank you to Professor Pandey. Probably we will take a picture before we leave. And could you, Guntur, could you help us how to take the picture?
Yes, Pak. Okay. I will. Wait, I will stop the YouTube stream first.
Yes.
Okay. So